Listeners, what was the wind turbine's opinion about sustainable energy? Well, it said, I'm a huge fan. Get it? A wind turbine is a huge fan that creates energy. And that is the topic of our first lesson for Advanced Subsidiary or AS level as you know it for Namibian learners today. A warm welcome to all NSSCAS geography learners and everybody else interested in learning more about the natural wonders of geography. We will have a series of 5 radio learning programs, and in lesson 1, we are discussing the Earth's energy budget. If you are a NAMCOL student, you will find this topic in your NAMCOL NSSCAS geography textbook in the chapter on physical geography, atmospheric processes. So, let's get started. Why do we have to learn about the global energy budget in school? What is the relevance of this topic to our lives? You may want to know. This is a good question. We need to know why we were studying something. Otherwise, it won't make any sense to us, right? Well, briefly, the Earth's energy budget describes the balance between the sun's energy reaching the Earth and the energy that flows from the Earth back out to space. Why is it important for us to study the Earth's so-called energy budget? The Earth atmosphere system is constantly trying to maintain a balance between energy reaching the Earth from the sun and energy that flows back from the Earth to space. If the system is changed, either through natural phenomena such as volcanoes or through human activities, an imbalance in the Earth's energy budget can occur. The consequences of this would be a rise or fall in the temperature of the Earth as it tries to restore its energy balance. This would be directly felt as changed weather and ocean circulation patterns on the Earth. The radiation balance on the Earth's surface is also critically important as it provides the energy needed to evaporate water at the surface, which determines how much rain can fall over the globe. We want to understand this so we can do our part to ensure humanity's survival on the Earth. Are those not good reasons to study this topic? I thought so. So, to start at the beginning, the atmosphere of the Earth gets energy from the sun, meaning that the sun is the main source of energy for the Earth's atmosphere. But about a third of the sun's incoming energy is reflected back to space by clouds, atmospheric molecules, tiny aerosol particles, and surfaces of the Earth like land, snow, and ice. This all reflects the sun's energy back up to space. But the Earth also generates energy, which it emits into space. This is thermal or heat energy, mainly from the infrared part of the electromagnetic spectrum. The intensity of thermal emission depends on the temperature of the surface. Now, just like a financial budget is an effort to get a balance between inflow and outflow of money, an energy budget tries to balance the amounts of energy entering a system, transferred within the system, and leaving the system. How does this movement of energy within the atmosphere work? How does it enter the system, transfer within the system, and leave the system? Let's see. We have given you a clue already. The sun produces radiant energy which travels towards the Earth's surface in the form of short-wave radiation. This is incoming solar radiation, also called insolation. But not all the radiation reaches the Earth's surface. Only about half of this radiant energy reaches us. Of this energy, 20% of it is absorbed by the atmosphere and clouds, while 30% is reflected back to the atmosphere. So, if the sun produces 100% of solar radiation, but only 51% is actually absorbed by the Earth's surface, what happens to the other half of this solar radiation? Well, the sun's radiant energy travels through space, bouncing against obstacles, reflecting or being absorbed by other obstacles, and losing energy because it cools down. Clouds absorb 19% of the sun's energy and reflect 20% into space. Water vapor, other atmospheric gases, and dust absorb another 19% and reflect back 10%. This leaves only about 51% of the original sun energy that actually reaches the Earth's surface. However, the Earth's surface then also reflects 6% of this energy back into space, a process known as albedo or reflective power. At the end of the long road from space to Earth, only 46% of this radiant energy is absorbed by the Earth's surface. Again, the incoming solar radiation is either reflected back into space or absorbed by clouds and other things before reaching the Earth's surface. The reflection of the sun's energy is known as albedos. Now you want to know what happens to the 46% of the solar radiation which gets absorbed by the Earth's surface, right? There are three things that happens to energy received by the Earth. First, the energy is converted to heat energy when it reaches the surface. As the ground warms, some is re-radiated as long-wave radiation called terrestrial or land radiation. Now, the three things. Around 8% of this re-radiation is lost to space. Another 25% of heat energy from the Earth is lost through evaporation and condensation when the water in lakes and oceans is turned into vapor. This is called latent heat transfer. And 7% of this re-radiated energy is absorbed by clouds, water vapor, and carbon dioxide. Now, you know something about incoming solar radiation and outgoing solar radiation to and from the Earth's surface. But are you aware that some parts of the Earth receive lots of solar energy while others receive little? Of course you do. Some parts of the Earth get a lot of sunshine, like ourselves in Namibia and other countries near the equator. These areas have a lower latitude and receive the greatest insolation. Sol for sun, remember? An area that are near the poles on the higher latitudes receive the least amount of insolation. The sun does not shine there as much, so it is colder there. This difference in the amount of the insolation received due to the difference in latitudes results in an imbalance in the energy budget of the globe. For a change, we are the haves. We have a lot of sunshine and sun energy, and the cold countries are the have-nots. The scientific way to describe this is that at lower latitudes, there is excess or surplus of insolation, creating a positive budget in these areas. At higher latitudes, there is a scarcity or a deficit due to less insolation, which create a negative sun energy budget in these regions. You may be wondering, do the equatorial regions, that is near the equator, where there is the most sunshine, experience overheating because of too much insolation? And can the opposite happen to the polar regions? This is a very good question, and it addresses our first learning objective. Briefly, the answer is no. Areas at the equator are not getting increasingly hotter at the extent that they overheat. No. Do the poles get progressively colder, although of the course they are already frozen? It works like this. The equator receives the greatest insolation because the sun strikes directly at it, meaning the rays of the sun travel a shorter distance to the equator and shines directly on a smaller area. On the other hand, the sun's rays must travel a longer distance to the poles and shine over a larger area to warm it up. The difference in the amount of insolation at the equator and at the poles will give an imbalance in the amount of heat between the two regions, which result in a horizontal transfer of heat between low latitudes and high latitudes to compensate for the difference in global insolation. The transfer of heat through the horizontal movement of air is called advection. How does it work? In order to move and transfer this energy around to create a better balance, the Earth uses ocean currents, pressure belts, and winds. They move cold temperatures from the poles toward the equator and warm temperatures from the equator to the poles. This is what prevents the poles from getting excessively cold and the equator from getting excessively hot. Let's talk about the cool transfer of heat energy. How does it move from one region to the other? Ocean currents take cold water from the poles towards the equator, such as our own cold Benguela current along our west coast. And warm water from the equator is taken to the poles, such as with the warm Mozambique current on the east coast of Africa. The wind and pressure belts, on the other hand, use wind. A westerly wind transfers air towards the poles to take warm air there. An easterly wind moves towards the equator, bring cold air down along the coast. Now we get to the big question. Why is it important for us to study the Earth's energy budget? This is because the regional distribution of incoming and outgoing heat energy across the globe drives the atmospheric and oceanic circulations or flows. In the tropics, more energy is absorbed than emitted, resulting in a surplus of radiant energy. At high latitudes, the opposite is true. The general circulation of the atmosphere and oceans transport heat from the warm tropic to the cold poles. Can you see that a change in the regional distribution of radiant energy would have a direct impact on weather and ocean circulation patterns? However, there are internal variations in the system associated with atmospheric and oceanic circulations that also cause Earth's energy budget to vary. To improve our understanding, the Earth's energy budget is observed over a range of time scales, from monthly to a few decades. Listeners, this wraps up our first lesson in a series of 5 for advanced subsidiary or AS level Namibian learners. We trust you will be now able to describe the Earth's or the global energy budget. You have heard and learned that the reflection of the sun's energy is called albedo. There is incoming solar radiation to the Earth's surface and outgoing solar radiation back into space. Only 46% of the sun's radiation of energy is eventually absorbed by the Earth's surface, as incoming solar radiation is lost in space through reflection, absorption, evaporation, and land radiation. In the exam, you can make use of a well-labeled diagram to show all the ways that energy is lost between the sun and the Earth's surface. You can also use a well-labeled diagram to describe how the absorbed heat and the Earth's surface is radiated back into space. Remember to indicate approximate percentage absorbed and reflected in each case. You should also be able to show and describe the movement of cold air and water from the poles to the equator, and of warm air and water from the equator to the poles. I look forward to speaking to you again. We will discuss the local energy budget in lesson 2. Until then,
this lesson is produced by NAMCOL with funding from the Ministry of Education, Arts and Culture.